Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. If you're new to this channel, be sure to check out the playlist with all the videos in this series, which I'll link to in a card in the corner of the screen. And I've realized recently that my cards may not be working because of a glitch with YouTube, but I'm just gonna keep going like they do work, and I'll figure out what's going on soon. Last week, we constructed the natural numbers using only concepts from set theory. This week, we're going to extend a similar type of construction to the integers, the rationals, and the reals. Hopefully, after this week's video, you'll understand a bit better how we can use set theory to create and formalize things we previously took for granted. But first, if you haven't watched last week's video, click on the card above to watch that first. The reason we're talking about the integers and the rational numbers, other than them being important for math, is to create a progression from constructing the natural numbers to constructing the real number line. With the natural numbers, we have a starting point, 0, and we take discrete, i.e. countable, steps in one direction, positive. With the integers, we still start at 0 and we still take discrete steps, but this time we're going in two directions at once, positive and negative. Then with the rationals, we have some conception of stepwise motion. For example, we know we can construct the sequence 1/2, 1/3, 1/4, and 2/2, 2/3, 2/4, but figuring out how to do it all at once is a little more complicated. And finally, the reals are just absolutely zany. We have to take infinitely small steps, and we have no obvious way to do so. But not to worry, because we can do that with set theory. Let's start with the integers, 1 degree of separation from the natural numbers. We denote the integers with a z, like this. There are many different ways to construct the integers from the natural numbers, but the one we're going to talk about uses equivalence classes. If you need a refresher on equivalence classes, click the card above to watch lesson 5. So say we have the number -3. Consider the equation x minus y equals -3. We can't graph this like we would a normal continuous function, but we can graph it on a lattice of points, where the x and y axes are the natural numbers. Our first point is here, at 0, 3. Our second point is 1, 4, and so on, in a line with slope 1. Every ordered pair of points on this line has a difference of -3, and we can do the same thing for all the rest of the integers. To formalize this construction, we define an integer k as the equivalence class of all the ordered pairs x, y, such that x minus y equals k, and x and y are natural numbers. Using this definition, we can create any integer as an extension of our previous construction of the natural numbers. We can do something similar to construct the set of rational numbers, q, using only the integers. This time, to create a given rational number, we will draw a line passing through the origin whose slope is equal to that rational number. We know we can do this for any rational number because we just have to find a lattice point, an ordered pair of integers, that the line passes through, in addition to the origin. If the slope is rational, we know that this point exists, and in fact, we know that an infinite number of these points exist. Formally, we define a rational number q as the equivalence class of all ordered pairs a, b, such that a divided by b is equal to q. Unfortunately, we cannot construct the set of real numbers as a set of equivalence classes of ordered pairs of rational numbers, or a similar sort of thing, and we'll talk about why that is more next week, but basically it's because there is no one-to-one correspondence between the natural numbers and the reals. With the integers and the rationals, we can still count them like 0, 1, -1, 2, -2, etc. But the set of real numbers is like a whole degree bigger in size than all of those countable sets. So if that's the case, how do we construct the real number line? Well, we use this thing called Dedekind cuts, named after a German mathematician named Richard Dedekind. To quote from the textbook's very good explanation, the idea behind Dedekind cuts is that a real number x can be named by giving an infinite set of rationals, namely all the rationals less than x. So basically, the idea is that x may not be a rational number itself, but there is a sequence of rational numbers that gets infinitely close to x. Because remember that unlike the natural numbers and the integers, the rationals are infinitely close together. So no matter how close a given rational number is to some real number x, you can always find another rational number that's closer. I'm not going to prove that right now, but I believe there is a really cool visual proof of this using something from number theory called a fairy series. So I'm going to try to find that online, and I will link to it here if I find it. So formally, a Dedekind cut is a subset x of q, the rationals, such that x is not the empty set and x is not q, So x is either nothing nor infinity. X is closed downward, that is, given rationals q and r, if q is in x, or q is less than x, and r is less than q, then r must also be in x. And finally, x has no largest member. It must be an infinite series that converges at some limit. As we can see, this supports our definition of a real number x as the set of all rational numbers that are less than x. Therefore, the set of all real numbers is simply the set of all Dedekind cuts. There is an alternate way to construct the real numbers using something called Cauchy sequences. It's a little harder to conceptualize, so I'm not going to go super into depth about it, but it's essentially a more general version of what we just did with the Dedekind cuts. We define a Cauchy sequence to be, first of all, a function from the naturals to the rationals. Another way to say this is, a Cauchy sequence is a sequence of rationals, an ordered list with a starting point and a direction. Furthermore, this sequence of rationals must converge. It can't go off to infinity or oscillate back and forth forever. It must get closer and closer to some fixed number, which is our target real number. Using this construction, we can define a real number x to be the equivalence class of all Cauchy sequences that converge to x. So the set of all real numbers is the set of all such equivalence classes. And that's pretty much it. I hope you enjoyed this video. Let me know what you think and if there's anything that would make it better. Thanks for watching. See you next week.